Let's take a look at Lesson 4, Trigonometry, which is special triangles, exact values, and developing the unit circle. So if you recall, we did go through special triangles a couple of lessons ago, and our special triangles evolved. We'll just take a reminder on that one. So our special triangles, the first one evolves from a square having side length of 1 unit. And what happens is we divide that square into 2 identical right isosceles triangles, and so from there we can get this triangle right here, and we can see that the side lengths are 1 and 1. Those are the 2 legs. My angles are 45 degrees, 45 degrees, and 90 degrees. When it's a right isosceles triangle, remember, anytime we have an isosceles triangle, when there's 2 lengths the same, there's 2 angles the same. In terms of our hypotenuse, then we can find that using Pythagorean theorem. So we know that 1 squared plus 1 squared will equal c squared, or the hypotenuse squared. And so that means that 1 plus 1 is equal to c squared, or c squared is equal to 2. So then we take the square root of both, and that tells us that c is equal to the square root of 2 in that particular case. If we take a look at then using SOHCAHTOA or standard trig ratios, then we know that the sine of 45 degrees is opposite over hypotenuse, or 1 over root 2. When we rationalize that by multiplying by root 2 over root 2 to get the radical out of the denominator, we end up with root 2 over 2. Cosine of 45 degrees is adjacent over hypotenuse, so once again, 1 over root 2. Rationalizing that becomes root 2 over 2. Tangent of 45 is opposite over adjacent, and therefore we're looking at 1 over 1, or simply 1. When we take a look at the other special triangle, is our 30, 60, 90 triangle. And where did that one come from is, once again, we're talking about it as an equilateral triangle that had side length 2, 2, and 2. And so if all side lengths are the same, then all angles are the same. So 60 degrees for all 3 angles. And then what happened though was we bisected the triangle by dividing it into 2 equal halves. So all of a sudden then our bottom length here is just 1 unit from here to here, which is our x value, or adjacent to our 60 degrees. The altitude, or the height, is going to be found using Pythagorean theorem again. So we know that r squared, if we say that our hypotenuse is r squared minus a squared is equal to b squared. So then 2 squared minus 1 squared is equal to b squared. So then that's 4 minus 1, which is 3. So b squared is 3, which means that b is equal to root 3. So that is our altitude, is root 3. This top angle here, because that's the third angle and all angles add up to 180 degrees, is going to be 30 degrees. So if we run through our basic trig ratios again, sine of 60 degrees is opposite over hypotenuse, so root 3 over 2, or sometimes we think about, instead of opposite over hypotenuse, y over r. Cosine of 60 degrees is adjacent over hypotenuse, or x over r, so 1 over 2. Tangent of 60 degrees is opposite over adjacent, or y over x, which is root 3 over 1, or simply root 3. When we take a look at diagram 3, what they're doing is they're showing an angle of 30 degrees in standard position. The triangle itself is obviously exactly the same as the triangle above. It's just been rotated, or we're looking at it from a different perspective. So if we take a look at this one, then again we know that opposite the 30-degree angle is length 1, and we can see that from going back to diagram 2. Opposite the 30 is the 1. As well, we know that this is the 60 degrees. Opposite the 60 degree, or adjacent to the 30-degree angle, is an x value of root 3. So we know this triangle, special triangle, has lengths 1, 2, and root 3. So sine of 30 degrees is again opposite over hypotenuse, or y over r, so 1 over 2. Cosine of 30 degrees is adjacent over hypotenuse, or x over r, so root 3 over 2. And tangent of 30 degrees is opposite over adjacent, so that's 1 over root 3. But again, rationalizing by multiplying top and bottom by root 3 gives us root 3 over 3. So let's move on then. So again, we talked about those special triangles. Really, you don't have to memorize all 3 of them, because we recognize that the third triangle is essentially just a rotation of that first triangle. If we take a look at trying to standardize that so that the hypotenuse length of for each one is 1 unit, then we can see that for this first triangle, to go from a hypotenuse of 2 to a hypotenuse of 1, we need to scale that down. So we will divide every length by 2. So then our height, or our y value, becomes 1 divided by 2, or 1/2. Our base length, our x, is root 3 divided by 2, or root 3 over 2. To go into that second triangle, our 45, 45, 90 degree triangle, that right isosceles triangle, because we have a hypotenuse here of root 2, a hypotenuse here of 1, so then we need to divide everything by root 2. So then this is 1 over root 2, or 1 divided by root 2, but rationalized it is root 2 over 2. And then the same thing obviously happens for that y value. That third triangle, exactly the same as the first, just reflected. So what we can do then is put together a little bit of a summary table. So for this, we're looking at it as r is equal to 1. And so we can either come up with these values of sine of 30 or cosine of 30, tangent of 30, by looking at this set right here, and I would advise you to do so at this point in time, just to see what happens. If you get stuck at all, obviously you can go back and you can look at the special triangles. They are exactly the same. It's just a scaled down version of itself. So hit pause, complete this table right here, and then when you're all done, come back and we'll compare answers. So you've completed the table, and if you used these triangles where the radius was equal to 1, what you would have recognized very quickly, I hope, is that sine of 30 degrees was opposite over hypotenuse. Well, because the hypotenuse was already 1, then it was literally just your opposite, or your y value. When we looked at cosine of 30 degrees, or adjacent over hypotenuse, or x over r, then adjacent to the 30 degrees, root 3 over 2 over 1. And once again, because the hypotenuse or radius is 1, then we're only looking at the x value conveniently. A little bit more difficult with these triangles when we have tangent of 30, because then it's opposite over adjacent, or 1/2 over or divided by root 3 over 2. So tan of 30, then if we're looking at the radius of 1, then that is y over x, or 1/2 over root 3 over 2. That, of course, can be rewritten, since it's a complex fraction, 1/2 divided by root 3 over 2, or 1/2 times 2 over root 3. The 2's cancel each other out, or we're looking at 2 when we multiply across, 2 over 2 root 3, so then that's 1 over root 3. If we rationalize that by multiplying by root 3 over root 3, then we of course get root 3 over 3. So tangent becomes a little bit trickier. That's where looking at the original special triangles might be easier for you. If we go down and we're looking at the finding exact trig ratios for angles of 0 degrees and 90 degrees, think about it as if r is equal to 1, if we're looking at 0 degrees, then that tells us that our terminal arm is on the positive x-axis. The easiest thing to think about is that our x value is obviously 1, y value is 0, and then r is equal to 1 here. So if we think about sine of 0, sine is equal to y over x, so, y over r, so that's 0 over 1, which is simply 0. Cosine of 0 is x over r, so that is then 1 over 1, which is 1. Tangent of 0 is y over x, so then that is 0 over 1. 0 divided by 1 is 0. If we look at 90 degrees, and then again, if we take a look, if this was the unit circle with a radius of 1, and so then our terminal arm is on the positive y-axis, then we're looking at coordinates of 0, 1, so x is 0, y is 1, and of course r is 1. So sine of 90 degrees is going to be y over r, so then that is 1 over 1, which is 1. Cosine of 90 degrees is x over r, or 0 over 1, which is 0. Tangent of 90 is y over x, or 1 over 0, but anything divided by 0 is undefined. And so why is tan of 90 undefined? We cannot divide by 0. So remembering again that rotation angle of 0 degrees is also going to be exactly the same as a rotation angle of 360 degrees. 90 degrees, however, will not be the same as 270 degrees, because if we look at if the terminal arm was on the negative y-axis, well, r is still 1 and x is still 0, but y is now negative 1. And so when does that change? Well, that's going to change when we have sine of 270 degrees, because that will then be y over r, or negative 1 over 1, which is negative 1. Let's take a look then at, again, another chart where they've added in 0 degrees and 90 degrees. They've indicated here that you should memorize this chart. I'm not all that concerned about you memorizing the chart. It's obviously useful if you have it, but I think that's also a lot of information to take in. All of the information that would be on the table is also easily accessible just by knowing your two special triangles. So if you know that you've got one of your triangles is your right isosceles triangle, which is 90, 45, and 45 degrees, and your lengths are 1, 1, root 2, and then your other triangle is your 90, 60, 30 triangle, and those lengths are 1, 2, root 3. So if you've got those two special triangles memorized, then all of that information can be found for your table. As well, you would also need to know that if the terminal arm was on any of your axes with radius of 1, then what are those corresponding x and y values? So obviously we're looking at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And so recognizing those along with the cast rule easily allows you to fill in that table. So it's totally up to you if you would like to memorize the table or if you want to memorize the triangles, but you will need one of those. So take a moment again, fill in the table, either using the triangles or through memorization, and hit pause and we'll come back and check. Okay, so we've completed the table either using the triangles or thinking it through as to what each of those values are, each of those trig ratios are. Perhaps you refer to the other tables that you previously completed. So a few things that you want to recognize. Sine ratios are increasing from 0 to 1. So we can see sine of 0 is 0 and sine of 30 degrees is 1/2. Sine of 45 is root 2 over 2, and sine of 60 degrees is root 3 over 2. So these values are getting bigger all the way up to sine of 90 degrees, which is 1. Cosine of these angles are exactly the opposite. So those cosine ratios are decreasing from 1 to 0, and the tangent ratios are equal to the sine ratio divided by the cosine ratios. But we also knew that because we knew that tangent of theta was always equal to y over x. So if we were using these, using the table to determine the exact value, so exact value means that we're not going to be able to use your calculator, because in some cases, any of those where we have a radical, we would end up with a decimal approximation using the calculator. So we want to use those exact values. We can again go back to the table. We can also use cast rule along with those special triangles. So in terms of the reference angle, sine of 210 degrees, we recognize that our reference angle is 30 degrees, and because sine of 210 degrees, when we see that that is in our third quadrant, and when we look at the cast rule, then sine of 210 degrees is going to be a negative ratio. So we can say then that sine of 210 degrees is going to be the same as sine of 30 degrees, except we'll take the negative of sine of 30 degrees. And sine of 30 degrees is equal to 1/2. So then sine of 210 degrees would then be negative 1/2. When I look at cosine of 300 degrees, again, when I take a look at it on the in the 4 quadrants, cosine of 300 is in the 4th quadrant. We can also see that the reference angle is 60 degrees. Cosine is positive in quadrant 4, so for that particular ratio, we recognize then that cosine of 300 degrees is going to be exactly the same as cosine of 60 degrees, because cosine is positive both in quadrant 1 and quadrant 4. Cosine of 60 degrees is 1/2, so cosine of 300 degrees is also 1/2. For tangent of 225 degrees, then 225 degrees is in quadrant 3, where tangent is positive, and our reference angle in this particular case is 45 degrees. And so since tangent is positive in quadrant 3 as well as in quadrant 1, then we know that tangent of 225 degrees will be the same as tangent of 45 degrees, and we can either go back to the table or we can look at our special triangles. Tangent of 45 degrees is root 2 over 2. Let's take a look at class example number 2. So without using technology, determine the exact values of theta, where cosine theta is equal to negative root 3 over 2, and theta is between 0 and 360 degrees. So we know that this ratio is negative, so the first thing that I'm thinking to myself is, well, where is cosine negative? Cosine is negative in quadrants 2 and 3. So I'll make a note to myself. I'm either talking about quadrant 2 or I'm talking about quadrant 3. If I'm looking at root 3 over 2, and let's say I don't have the table memorized, I'm thinking about my triangles. Which of my 2 triangles has the value root 3? And that's going to be the 30, 60, 90 triangle. So again, I'm going to sketch that triangle out for myself. and we have 30 degrees and 60 degrees, and 1, 2, root 3. The opposite of 30 degrees is going to be the shortest length, which is 1. The longest length is, of course, your hypotenuse. That measures 2. So if I'm looking at cosine, and cosine is adjacent over hypotenuse, so what length? Root 3 therefore must be adjacent to the angle. Root 3 is adjacent to 30 degrees, and that tells me that my reference angle is 30 degrees. So if my reference angle is 30 degrees, I'm in quadrant 2, then that tells me that my angle is 150 degrees. If I'm in quadrant 3, then and my reference angle is 30 degrees, then the angle must be 210 degrees. If we look at part B, it says tan of B is undefined. So I know that's one of these special circumstances. So in order for that to be undefined, it has to be, well, we know that tan of theta is always equal to y over x. So that means that undefined tells us x is equal to 0. When is x 0? That happens when my terminal arm is either on the positive x side or on, whoops, sorry, got myself mixed up there. So we're actually talking about the positive y-axis or the negative y-axis, and that's when we see x equal to 0, y is either equal to 1 or negative 1, and so that tells us that theta must be either 90 degrees or 270 degrees. If we look at class example number 3, we've got the point P negative 3 root 3 on the terminal arm of angle theta. So without using technology, and we can see that we've got some exact values here, so we want to draw the angle in standard position. So angle in standard position means that I'm looking at where that terminal arm is. That terminal arm is going to be in quadrant 2, so at negative 3 root 3, so that is approximately point P right there, and the angle in standard position is starting from our terminal arm, which is our positive x-axis. So this is our angle in standard position here. State the values of x and y, so obviously x is equal to negative 3, y is equal to root 3, and the value of tan theta, that is looking at the ratio, so tan theta is equal to y over x, which is negative root 3 over 3. So even though it's the x value that's negative, remember that we typically want to have that negative either in the numerator or out front. So stating the reference angle and hence the rotation angle. So again, if you know your table, then you can quickly look that up. So if I go back to the table, I'm looking for root 3 over 3, and we can see here tan of 30 is root 3 over 3. So that tells me that my reference angle is going to be 30 degrees. If we're not sure that it's, if we don't know the table, then again, you're referring back to your special triangles, recognizing that root 3 is in your 30, 60, 90 triangle. So we know that the reference angle is 30 degrees, and because we're in quadrant 2, then the rotation angle theta must be 150 degrees. Okay, so in terms of creating the unit circle, what are we looking at is the unit circle is a circle essentially that has radius of 1, and so we're going to take these special triangles that have r equals 1 or hypotenuse equals to 1, and we're going to place them onto the axis, and you can see that they've kind of dotted in what that circle is going to look like. So for our 30-degree triangle, or 30, 60, 90 triangle, which is this one, then if I trace this out, what we can see is that x value then is root 3 over 2, so root 3 over 2. The y value is that height, which is 1/2, and that is for 30 degrees. If we look at the next triangle, which is our 45 degree, 90 right isosceles triangle, so we've got that as 45 degrees, and both the x and the y values are root 2 over 2. Again, that's been rationalized from 1 over root 2. If we look at the next triangle, which is really the same as our first triangle, just rotated around, and so that is our 60, 30, 90 degree triangle. And so again, we know that the x value, the width here, or the adjacent to the 60 degrees is 1/2. They've already gotten that written out. And the height, or the y value, is root 3 over 2. And so that's for 60 degrees. We can also add in as well when it is on 0 degrees or 360 degrees, then that point is 1 and 0. And when we're looking at 90 degrees, x is 0 and y is 1. Okay. And so what should we recognize then in every single case is, if we think about cosine of 30 degrees, that is root 3 over 2. Sine of 30 degrees, we know, is 1 over 2. Well, conveniently, if we look at these, the ordered pair, it is root 3 over 2, 1 over 2. So it looks like that x value, x coordinate, seems to match with cosine of 30. The y value matches with sine of 30. If I look at cosine 45 degrees and sine of 45 degrees, again, they are the same, and they are exactly the same as the x and the y coordinates. Again, if we look at cosine of 60 degrees and the sine of 60 degrees, once again, they match up with the corresponding y and x coordinates for 60 degrees. So what we want to recognize is why people do like this unit circle is because in every case, when r is 1 on that unit circle, we have sine of theta equal to y, cosine of theta is equal to x. And so really what are we looking at is for a point x, y, really that point is cosine of theta followed by sine of theta. And since tangent of theta is y over x, then tangent of theta is sine over cosine. So these are important to note for sure. Let's take a minute to go back to the unit circle. And so I mentioned that some people will go and make the effort to memorize the unit circle. It looks pretty overwhelming for sure, but at the same time, it's actually fairly straightforward when you think about it, because if we recognize that for 30 degrees, if that's our reference angle, then 150 degrees has the same reference angle, as does 210 degrees, as does 330 degrees. If we take a look at the coordinates for these four angles that all share the same reference angle of 30 degrees, well, what do we notice about the x and y values, or the cosine and sine of those values? They're actually all the same, with the exception of some positives and negatives. How do we determine which are positive, which are negative? Well, we can do that in a few ways. One, we can recognize that in quadrant 1, we always have positive x, positive y. In quadrant 2, we always have negative x, positive y. In quadrant 3, we always have negative x, negative y. And quadrant 4, we have positive x and negative y. Alternatively, we also know that we're talking about x is also the ratio for cosine of theta. Y is also the ratio for sine of theta. Well, in quadrant 1, both cosine and sine ratios will be positive. In quadrant 2, cosine, which is our x, is negative, sine is positive. In quadrant 3, both cosine and sine ratios are negative because that is a quadrant where tangent ratio is positive. And in quadrant 4, cosine ratio is positive and sine ratio is negative. So there's a few ways that we can go through that. So you don't actually have to memorize all 4 quadrants. If you were to know one quadrant or quadrant 1, then that would be enough to be able to determine the other 3 quadrants. For this year, you won't actually need to memorize a unit circle. You will need to know it next year. This year, certainly, having those special triangles will be sufficient. So let's look at some other examples then. If we take a look at class example number 4, it says use the unit circle to find the exact values of the trig ratios for a rotation angle of 240 degrees. Give each answer with a rational denominator. So sine of 240 degrees, we know that that would just be the y value. So let's just go back to that unit circle and look at 240 degrees. 240 degrees is negative 1/2 negative root 3 over 2. So if I know that 240 degrees, it's negative 1/2 and negative root 3 over 2. I recognize that we're always looking at, on the unit circle, cosine theta followed by sine of theta. Then sine of 240 degrees is going to be negative root 3 over 2. Cosine of 240 degrees is then going to be negative 1/2, and that's pretty straightforward to do. Tangent of 240 becomes a little bit trickier. Why? Because now we have to look at y over x, or negative root 3 over 2 divided by negative 1/2, and that means negative root 3 over 2 divided by negative 1/2, or negative root 3 over 2 times negative 2 over 1, which is simply going to be root 3. Alternatively, if you weren't using the unit circle, what is it that you would need to do is we need to go to our reference angle, and we would recognize that the reference angle is 60 degrees, in which case we can take our special triangle that has 60 degrees in it, and we know that it's 1, 2, root 3, and we recognize that we're in quadrant 3 in this particular case, and therefore quadrant 3 tangent is positive, cosine and sine ratios are negative, and we can find exactly the same values. So you don't have to go to the unit circle. You can use the cast rule, reference angles, and your special triangles to find out exactly the same thing. Okay, let's take a look at class example number 5, and it says use the unit circle to find those exact values. So you may use the unit circle, or you may use your special triangles and the cast rule and reference angles. So take a moment, fill those out, and we'll compare. Hit pause and we'll compare in a moment. So let's take a look at our answers. So cosine of 135 degrees, if I'm using the unit circle, then I'm simply going back and I'm looking for that x coordinate for 135 degrees. If I'm not using the unit circle, then I think to myself, what is the reference angle? It is 45 degrees, and it is in quadrant 2. Because it's in quadrant 2, cosine is going to be negative. So cosine of 135 degrees will be just the same as cosine of 45 degrees, except negative. And I can draw out my special triangle and see that adjacent over hypotenuse, or x over r, is negative root 2 over 2 once it is rationalized. So same thing with tangent of 120 degrees. For sine of 180 and tangent of 270 degrees, we recognize that those are actually on the axes themselves, so 180 degrees. For that, we know that x is 0 and y x is -1, and y is 0, so y over r is 0 over 1, which is 0. For tangent of 270 degrees, then we're down on the negative y-axis, and in that particular case, x is 0 and y is -1, so then y over x for tangent is -1 over 0. Anything over 0 is undefined. If we look at class example number 6, I've got points A and B, 2 points on the unit circle. And so we can see that with a quick sketch, we're looking at A is -x, +y, so it's obviously in quadrant 2. X and y values are basically equal, which tells me that that is going to be at a 45-degree angle. So A then has a reference angle of 45 degrees, and that means that if it's a reference angle of 45 degrees, that A must be at 135 degrees if it's in quadrant 2. For B, we're going into -x and -y, and that means that we're in quadrant 3. So if I go -1/2, but -√3 over 2, which is something that is greater than -1, less than, I guess, since it's negative, but √3 over 2, when we look at both the positives, √3 over 2 is greater than 1 over 2, and so that is a reference angle of 60 degrees. We're in quadrant 3, and so this is point B. So B is going to be with a reference angle of 60 degrees. That tells me that that is 240 degrees. If we're going counterclockwise around our unit circle, then from 135 degrees to 240 degrees, then we know that the angle of that rotation is going to be 240 minus 135, and that is 105-degree rotation. And that's counterclockwise. We also know it's counterclockwise because it's a positive angle. Alternatively, I could have written just positive 105 degrees. If we take a look at class example number 7, and it says use a calculator to determine to 4 decimal places the coordinates of the point on the unit circle corresponding to a rotation of 148 degrees. The key words here is being that it is on the unit circle, and we know that for anything that is on the unit circle, that it will always be cosine theta followed by sine theta. So that means in this particular case, we're going to fill in cosine 148 degrees and sine 148 degrees. So we just need to ensure that our calculator is in degree mode and punch those in, and we've got our ordered pair. So let's take a look at that then. And so you'll see we've entered cosine 148 degrees on our calculator and sine of 148 degrees into our calculator, and we've got those two ratios, and those are approximations based on what our calculator can give us. Because they don't have reference angles that are related to our special triangles, then we have no exact values that we can find at this point in time. So these are the values that we want to use, both rounded to the nearest 10,000th or 4 places then. So let's fill that in. So then that would be -0.8480 and 0.5299. So for class example number 8, we're doing just the opposite. So it tells us that it lies on the unit circle, and so again we recognize that cosine of theta must equal -0.8829, and sine of theta must equal 0.4695. And the nice thing is that you can use either one to figure out what your reference angle is. You could choose one and then use the other one to double check your work. Because the x is negative, the y is positive, then we know that we are also dealing in quadrant 2, so that's also good to note. I would always use the inverse of the positive value, because that will always give you your reference angle. So I know that my reference angle can be found by doing the cosine inverse of positive 0.8829. Alternatively, we can do the inverse sine of 0.4695. Regardless, I should come up with the same reference angle, and we can put that into our calculators then and figure that out. So inverse cosine of decimal 8829, and that gives us an angle of reference angle of 28 degrees. Alternatively, it was 4695, so the second sine of 0.4695. And so again, we can see we come up with exactly the same angle, which is 28 degrees, but because we're in quadrant 2, that tells us that theta in our angle in standard position must be 152 degrees. So complete the assigned questions and recognize that you have a few ways to go through it. Either way, something unfortunately needs to be memorized. You'll either need to memorize the table or the unit circle, the first quadrant of that at least, or just your two special triangles. My personal advice for now would be to start with those special triangles, and then next year you can move into memorizing the unit circle. So if you have your special triangles down pat and you know how to use reference angles and the cast rule, you will be just fine. So please let me know if you have any questions.